Cardinality compares sets by functions. Two of its most important theorems say which functions are impossible, and which ones are enough. Cantor proves that every power set is strictly larger than its original set. Schroder Bernstein proves that opposite injections force a bijection. Apparently infinity enjoys making simple comparisons look suspicious. The power set of A, written script P of A, is the set of all subsets of A. For A equal to the set containing 1, 2, and 3, the power set contains these 8 subsets. A set with 3 elements has 8 subsets. More generally, a finite set with n elements has 2 to the n subsets. Cantor's theorem says the power set remains larger even when A is infinite. Counting the subsets one by one is not a promising career plan. Cantor's theorem states that for every set A, the cardinality of A is strictly smaller than the cardinality of its power set. One direction is easy. Send each element A to its singleton set. This is an injection from A into the power set of A. The real claim is that no function from A to its power set can be surjective. Notice the strength. Not merely no obvious function. And not merely no bijection. Every attempted list of all subsets must miss at least one. Suppose, for contradiction, that F maps A onto its entire power set. Define D to contain exactly those elements A that do not belong to F of A. This set is built to disagree with every listed subset F of A, specifically at the element A. Because F is supposedly surjective, some element D must satisfy F of D equals D. Now ask whether D belongs to D. By definition, D belongs to D if and only if D does not belong to F of D. But F of D equals D. So D belongs to D if and only if D does not belong to D. Contradiction. Achieved with admirable efficiency. Therefore no surjection, and hence no bijection, exists from A to its power set. The singleton injection now proves the strict inequality. Cantor's theorem can be repeated. Take a power set, then its power set, and continue. Each step strictly increases cardinality. Consequently, there is no largest cardinality, given any proposed largest size. Its power set ruins the proposal immediately. For the natural numbers, each subset is encoded by an infinite 0-1 sequence, recording non-membership or membership. Thus the power set of the natural numbers has cardinality 2 to the Aleph 0. Which is strictly greater than Aleph 0. The Schroder Bernstein theorem says that if A injects into B and B injects into A, then A and B have the same cardinality. It is also called the Cantor Bernstein theorem. Write the two injections as F from A to B and G from B to A. The maps F and G need not be inverses. So we must construct a new bijection. Two one-way tickets do not automatically form a return ticket. There is a useful graph picture. Put A on the left, B on the right, and draw edges for both injections. Injectivity prevents two arrows of the same type from merging into one target. Adding the G edges breaks the graph into chains and cycles, alternating between A and B. On each component, one can match every A element with a B element by choosing the correct direction consistently. The formal proof packages that component choice into a sequence of subsets. This looks less charming, but it is much easier to verify. Let F inject A into B, and let G inject B into A. Define A naught to be the elements of A that do not lie in the image of G. Recursively define AN+1 by sending AN forward through F and then back through G. Let C be the union of all these layers, starting from A naught. Now define H from A to B on C. Use F forward. Outside C use G inverse backward. The formula is short. The proof is the entirely reasonable process of checking that every symbol in it actually behaves. First, if A is outside C, why is G inverse of A even defined? A naught is one of the layers in C, so A outside C cannot belong to A naught. But A naught is exactly A minus the image of G. Therefore A must lie in the image of G. Since G is injective, exactly one element B satisfies G of B equals A. Thus the second branch of H is well defined. A formula using an inverse has now earned the right to exist. Within C, H equals the injective map F. Outside C, H equals the inverse of the injective map G. So it is injective there as well. The only possible problem is a collision between the two branches. Suppose C is in C, A is outside C, and both branches hit B. Then A equals G of B, which equals G of F of C. Because C lies in some layer AN, G of F of C lies in the next layer AN plus 1. And therefore lies in C. This says A lies in C, contradicting our choice of A. The two branches cannot collide. So H is injective. To prove surjectivity, take any B in B and examine the point G of B in A. If G of B lies outside C, the backward branch gives H of G of B equal to B. If G of B lies in C, it cannot lie in A naught, because it is already in the image of G. So it lies in some later layer. Thus G of B equals G of F of A for some A in the preceding layer. Injectivity of G gives B equals F of A. Since A lies in C, H of A equals F of A, and hence equals B. Every B has a preimage under H. Therefore H is both injective and surjective, which proves the Schroder Bernstein theorem. As an application, the open interval and the closed interval have the same cardinality. The inclusion map injects the open interval into the closed interval. In the other direction, send x to x plus 1, divided by 3. Its image is the closed interval from 1/3 to 2/3, safely inside the open interval. We now have injections both ways. So Schroder Bernstein guarantees a bijection without requiring us to write that bijection explicitly. This is why adding two endpoints changes the set but not its cardinality. Infinity has once again declined to respect finite bookkeeping. Cantor's diagonal set differs from every attempted entry in a list, proving that a power set is always strictly larger. Schroder Bernstein turns injections in opposite directions into a bijection by using F on the forward layers and G inverse everywhere else. Together, the two theorems provide the basic machinery for proving both strict cardinal inequalities and cardinal equalities.